Ask an AI to build a payment API and it will scaffold the endpoints in 4 minutes. Clean code, passing tests. What it will not give you is the system that handles a debit without credit failure at 2 crore transactions per hour without losing a single rupee. This is exactly the constraint PhonePe faced when scaling to 500 million users. Generating the API is free. Designing the system that never drops a transaction is the job. 5 things you will own after this video. The 3-party UPI model, the NPCI central switch, the payment layer stack, the PostgreSQL versus NoSQL trade-off for financial ledgers, and the 5-phase interview framework to design PhonePe in 45 minutes. Watch this video to the end because understanding this single decision is the difference between a junior developer and a senior engineer. Let us build it. Here is the biggest misconception about fintech. Users think PhonePe moves the money. It does not. PhonePe is just a messaging layer. It is a highly optimized remote control for your bank account. When you initiate a payment, PhonePe talks to the National Payments Corporation of India or NPCI. The NPCI is the central switch. It is the interoperability layer that connects every bank in the country. NPCI takes the message from PhonePe, translates it, and tells the sender's bank, say SBI, to debit the account. It then tells the receiver's bank, say HDFC, to credit the account. The banks hold the actual ledger. PhonePe orchestrates the messaging. The engineer who understands this separation of concerns is the one who designs the retry logic correctly. Let us trace the flow when you scan a QR code. The request hits the PhonePe backend. PhonePe must resolve that virtual payment address into a real bank account. Doing a database scan takes too long. It hits a Redis cache, resolving the VPA in under 1 millisecond. The resolved payload, wrapped with a secure idempotency key, is forwarded to the NPCI switch. This is where the heavy lifting of interoperability happens. Let us look inside the PhonePe backend. Layer 1 is the API gateway. This handles authentication, UPI PIN validation tokens, and rate limiting. It protects the internal services from traffic spikes during a Diwali sale. Layer 2 is the payment service. This is the brain. It enforces idempotency, ensuring that a retried network request does not result in a double charge. It generates the unique transaction ID before talking to the outside world. Layer 3 is the ledger storage. This must be a relational database like PostgreSQL. Why? Because financial transactions require strict ACID guarantees. If the write fails, the entire transaction must roll back atomically. Here is the architectural judgment. AI gets wrong. If you ask an AI to design a scalable app, it defaults to a NoSQL database like Cassandra or MongoDB because they shard easily. But you cannot use a NoSQL document store for double entry accounting. Financial data requires strict ACID guarantees. You trade the easy scalability of NoSQL for the absolute correctness of PostgreSQL. In payments, accuracy is non-negotiable. You have seen every layer and every trade-off. Let us put it all together one final time. The full system in one clean view. Hop 1. The user scans a QR code. The request hits the API gateway. Hop 2. The gateway handles rate limiting and forwards the request to the payment service. Hop 3. The payment service hits Redis to instantly resolve the VPA. Hop 4. A transaction record is initialized in PostgreSQL with an initiated state. Hop 5. The service wraps the payload with an idempotency key and routes it to NPCI. Hop 6. NPCI coordinates the debit and credit across the core banking systems. Hop 7. The response comes back and the ledger updates to success. You now own the architecture. Last piece. How do you walk an interviewer through this in 45 minutes? That is next. The 5-phase interview framework. Phase 1. Requirements. You must pin down the scale. 100 million daily transactions and the absolute constraint, zero money loss and strict consistency. Phase 2. Estimates. Calculate that 100 million daily transactions means about 1200 transactions per second on average, but easily 5000 at peak. Phase 3, high-level design. Draw the three-party model. Clearly separate the API gateway from the payment service and show the NPCI boundary. Phase 4, deep dives. Do not describe every component. Focus on how you generate idempotency keys and how you handle NPCI webhooks versus polling. Phase 5, trade-offs. This is where you shine. Explain why you rejected Cassandra in favor of PostgreSQL for the ledger, even though it is harder to scale. Before this video, a payment system was just an API endpoint that updated the database row. After this video, you know that a payment system is a distributed messaging coordinator enforcing strict financial contracts across government switches and legacy bank mainframes. Every engineer who draws PhonePe's payment architecture from memory is a senior engineer in the room, regardless of their title. AI writes the code, you design the system that never loses a rupee. In the next episode, we double click on the UPI payment flow, one wrong routing decision in the dual leg architecture. And PhonePe's payment fails for 10 million users simultaneously. We will learn how to design it correctly. Subscribe to ByteLearn for the complete PhonePe system design survival series. Hit the bell. Question: what is the most dangerous point of failure in this three-party architecture? Let me know below.